Assalamualaikum and good day everyone. In this video, we're presenting our M8668 group project titled Bus Schedule Pickup Routes. This is our team members, Nur Alfa Atira, Aina Itina, Hazira Afrina, Nur Shamiza, and me myself, Sophia. Throughout this presentation, we will explain how graph theory can be applied to model and optimize the bus pickup route network to improve transportation efficiency and support sustainable development. Without further ado, let's begin with the introduction.
Moving on to the introduction, public transportation requires efficient bus pickup routes to ensure passengers are collected on time while reducing travel distance and operating costs. However, poorly planned routes can increase fuel consumption, travel time, transportation costs, and also the carbon emission. In this project, the bus pickup system is modeled using graph theory, where bus stops are represented as vertices and routes are represented as weighted edges based on the distance. Next, the problem statement. So the main problem is that many bus pickup routes are not planned using the most efficient network, and routes planning become more difficult as the number of pickup locations increase. Therefore, this project applies the minimum spanning trees algorithm to determine the minimum distance network that connect all pickup points, improving operational efficiency while supporting sustainable
This network
transportation.
is also represented using the distance adjacency matrix. In this matrix, each row and column represents a bus stop. The numbers indicates the traveling distance between directly connected locations, while the infinity symbol indicates that no direct connection exists between those locations. This matrix provides a structured mathematical representation of the network and will be used in the next section when applying the graph algorithm to determine the optimal bus pickup route.
Okay, next is for the algorithm application. So we applied Kruskal algorithm to determine the minimal spanning tree for the bus route network. So the first step is to sort all possible bus routes according to their distance, from the shortest route to the longest one. The algorithm always consider the shortest available routes first because our objective is to minimize the total travel distance. So here is the list of the edges and also the weight. Okay, the second step is to iterative selection, where we examine each route one by one. So the first one is the route between the S4 and S5 with distance 2, where we add it to the tree because it creates no loop. And then same goes with the next route between S7 and S8, where we add because it creates no loop. And then the algorithm continues by selecting the next shortest route until we achieve step 7. And then when we check for the route between S4 and S7, we notice that it creates loop between uh, S4, S5, and S7. Therefore, we reject it. And then we also add route from S8 and S10, and also a route between S6 and S8 because it creates no cycle. And then we reject others since it creates loop or cycle. So therefore, 9 agents have been chosen, uh, which is exactly one less than the number of the nodes, which is 10. So that means that all the 10 bus stops are connected through the minimum possible total distance, completing the minimum spanning tree.
Now let's take a look at the result of our optimization. By applying Kruskal algorithm, we successfully stripped away the redundancy in our original map. Originally, the road network required a massive 66 km of potential infrastructure coverage. As you can see highlighted in blue on the slide, our minimum spanning tree successfully connected all 10 essential bus stops using just 9 strategic road links. Okay, this brings our total optimized network distance down to exactly 30 kilometers. Okay, to achieve this, we use Python to apply Kruskal algorithm efficiently. Using Python allows us to represent the entire transit network as a digital graph. Okay, sorting every potential road link by its distance in seconds. The script then systematically evaluate each connection, instantly accepting the shortest path while automatically filtering out loops and redundancies.
Now I will discuss the finding of our study. After applying the Kruskal minimal spanning tree, we successfully reduced the road network from 66 km to 30 km. This means the total distance was reduced by 36 km, which is about 45.5 reduction. Although the total distance became much shorter, all 10 bus stops remain connected. This is because the algorithm selected only the essential road and avoid putting unnecessary loop, making the network more efficient. This optimization provides several important benefits. First, it lowers the road construction and maintenance costs. Second, the bus consumes less fuel due to the shorter travel distance. As a result, it also helps to reduce carbon dioxide emission, making the transportation system more environmentally. Finally, shorter routes allow bus to travel faster, improving the overall efficiency of the bus service. For example, the route connecting Medical Centre, S4, High School S5 and East Riverside S7 form an efficient connection within the optimized network, showing how the algorithm identifies the shortest and most practical routes. So next, in conclusion, the project showed that the Kruskal minimal spanning tree algorithm is an effective way to optimize the bus route. By using this algorithm, we reduce the total route distance and while keeping all the 10 bus stops connected. This also helps to reduce travel distance, fuel consumption, transportation costs, and environmental impact. In the future, the system can be improved by combining it digital algorithm and passenger demand data to create even smarter bus routes. So that's all from us. Thank you.